Hi, welcome back to Mr. Chemistry. This is Nuclear Chemistry Mass Defect and Binding Energy Lesson 1. Okay, there's a couple things we need to know before we actually do this problem. What is mass defect? Mass defect is defined as the difference between the mass of the nucleus and the total sum of the mass of the nucleons. Oh, what are nucleons? Well, they're defined as either protons or neutrons, which belong in the nucleus of the atom. There are three basic pieces of information needed to determine the mass defect when you do the calculations. You have to have the actual mass of the nucleus that you're working with, the number of protons and neutrons in the nucleus, okay, so you got to know those numbers, and then you have to know the mass of the protons and neutrons themselves. Alright, so the mass defect equation is delta M equals, in parentheses, Z for the atomic number, MP, which is the mass of the proton, plus the neutron numbers times the mass of the neutrons, end quote, minus M nucleus. Again, Z is atomic number of protons, N is the number of neutrons, M little n is the mass of the neutron, M little p is the mass of the proton. The mass of the neutron is 1.00867 AMU, which was determined already. MP is the mass of the proton again, which is 1.00728 AMU, which was already determined. The mass of the nucleus, or M nucleus, equals mass of the nucleus. 1 AMU is equal to 1.6606 times 10 to the negative 27 kilograms. Sometimes people call it 1.66 times 10 to the negative 27 kilograms, but it really doesn't matter. And then, of course, mass into energy equation, the famous Einstein equation, E equals mc squared. All right, so now let's look at this one problem that we got here. That's a lot of information to digest, you know. So I want to try to go slowly with this problem here. Given the element copper 63, what is the mass defect if copper 63 is 62.91367 AMU? How much binding energy is produced? Okay, so we're trying to find the mass defect in the binding energy. So we're going to use first of all, we're going to use the equation that we found out for mass defect, which is going to be delta M equals Z MP plus N MN minus M nucleus. Alright, so now we have that there. This looks a little bit better because it looks a little strange there. Okay, so there we go. So what we're going to do is we're going to go ahead and do this thing. Well, now we know it's copper 63. That's the atomic mass unit. That's the number of protons and neutrons in the nucleus of the atom. So when we look at copper 63, right, we go 63 minus 34 neutrons will give us the number of protons, which are 29. We could have also done that by looking at the periodic table, because copper is element 29. Okay, so I just wanted to be a little fancy there. So I go delta M equals the number of protons, which was 29, times the mass of the protons. So we got 1.00728 plus the number of neutrons. Well, we knew that was 34, right? 34 times the mass of the neutron, 0.00, I believe that was 867. Yeah. And I should really be putting A and U in here. I'm sorry about that. I should have done that. And then we're going to close this entire bracket system here, minus the nucleus, which was determined to be 62.91367. Okay, dokie. All right. Let's make that 9 a little bit better there. I mean, we're not in a hurry. So let's go do that 9 there. All right, and then we're going to call that also AMU, right? So now we go and do the math. So delta M equals 29.2112 AMU plus 34.29478 AMU, okay, minus 62.91367 AMU. All right, so far, not too bad, you know, doesn't look that hard. So let's see here, we go delta M by the mass defect now equals 63.5059 AMU. We got that by adding those two together, minus 62.91367 AMU. All right, so our mass defect is actually equal to 0.59223 AMU. So we're almost done. We got half the problem done. So now what we need to do to determine the binding energy, the first thing we have to do is take that mass defect, which is an AMU, and convert it into kilograms, right? So we know that 1 AMU is equal to 1.6606 times 10 to the negative 27 kilograms. So now what we're going to do is we're going to convert this to 0.59223 AMU times 1.6606 times 10 to the negative 27 kilograms all over 1 AMU. AMUs cancel out, and this is going to give us our new mass defect in kilograms. And that's going to equal 9.831018 times 10 to the negative 28 kilograms. Wow, looks like we're running out of room here. Now, the next thing we're going to do is we use that famous formula E equals MC squared. All right, a couple things you need to know. All right, well, first of all, we're going to go energy. So E equals, let me go make a better equal sign. You know, let's make it fancy. What do you say? Why not? So we're going to go, there you go. E equals MC squared. All right, now that we have E equals MC squared, let's go ahead and plug in our information. So we go E equals our mass, which we calculate to be 9.83108 times 10 to the negative 28 kilograms. We'll put that in there, 9.83108 times 10 to the negative 28 kilograms times the speed of light squared, which is 3.0 times 10 to the 8 meters per second squared, right? There you go. And so when we do the math, it's going to E equals 9.831018 times 10 to the negative 28 kilograms times 9.0 times 10 to the 16 meters squared second square. And our final answer is going to be 8.8387 times 10 to the negative 11 kilograms times meter square over second square. Or you could just write this as E equals 8.8387 times 10 to the negative 11 joules. And that's it. You guys be snarly. I will see you back here at Musin Chemistry.